In this video, we are going to tackle a projectile problem that might look a bit daunting at first glance. There's a classical type of question that asks whether an object will be able to land on a target or fly right over it. For this kind of problem, the real challenge usually isn't the math itself, it's figuring out how to turn a general, open-ended question into a specific, solvable task. Once we can visualize what is happening and set a clear goal for what we need to find, the actual physics starts to fall into pieces. So let's walk through how to frame this problem and build a strategy to solve it. We have a setup where a snowball is being launched from the top of one building, and we want to know, is it going to land on the top of the second building? Before we dive into the formulas, let's think about our strategy. You might be wondering, how do I know where the snowball lands if I don't know the horizontal distance yet? Well, you're right, we don't know the horizontal distance, but we do know one thing for sure. If it lands on that roof, its vertical height must be 25 meters from the ground, which is the height of the second building. Since it was launched from a building that is 12 meters high, we can see the required vertical displacement, or delta y, is 25 meters minus 12 meters, which is 30 meters. So our strategy is simple. We want to find out exactly where the snowball is horizontally at the very moment it reaches that 30-meter displacement in y direction. If we visualize the path of the snowball, it follows a downward opening parabola. And this means that throughout its flight, the snowball will actually pass the 30 meters displacement twice, right? So the first time, let's call it delta t1, occurs right after the launch, while the snowball is still in the rising phase. And at this time, it reaches a horizontal distance of delta x1. The second time, let's call it delta t2, occurs after the snowball passes its peak and enters its descending phase. And at this time, it reaches a horizontal distance of delta x2. So which delta x are we looking for? Clearly it's delta x2, right? During the first interval, delta t1, the snowball is still surging upward. It cannot land on a flat roof while it's still climbing. It only has the chance to hit the top of the second building when it starts coming back down at delta t2 and its height drops to that 30-meter mark relative to the launch point. This means when we do the math, we are actually going to get two different answers for the horizontal distance, delta x1 and delta x2. But for our landing scenario, delta x2 is the one that we are really interested in. Once we calculate this horizontal distance, delta x2, for the descending phase, we can compare it to the position of the second building. If delta x2 is less than 150 meters, let's sketch out the trajectory of the snowball. I'm going to clear away some of these extra lines because the diagram is getting a bit cluttered. Okay, so if delta x2 is less than 150 meters, the snowball dropped to the roof's head before it even reached the building, so it will likely smack into the side wall. If delta x2 is greater than 185 meters, which is the near edge of the second building, plus its 35 meters width, it will fly right over the roof and land somewhere far beyond. So if delta x2 is greater than 150 meters plus 35 meters, which is 185 meters, the snowball will fly over the roof. If delta x2 falls anywhere between 150 meters and 185 meters, then congratulations, the snowball has landed safely within the landing zone. So as long as we get delta x2 is greater than 150 meters and less than 185 meters, we can conclude that the snowball will land on the roof. Alright, now that we've translated this into a clear task, which is finding the horizontal displacement delta x when the vertical displacement delta y equals 30 meters. right? Now we are ready to dive into the algebraic formulas and the math. The motion in horizontal direction follows a very simple rule. The distance traveled, delta x2, or the horizontal displacement, is just the speed multiplied by the time. The speed here is our initial horizontal velocity, Vix, which never changes throughout the entire flight. So our equation is simple. Delta x2 equals Vix multiplied by delta t2. We are given the initial total velocity, Vi, which is 45 meters per second, and then we can use a little bit of trigonometry to find Vix. So the piece of puzzle we are missing right now is delta t2, which is the time the snowball is in the air until it hits the roof on its way down. To find that time, we have to resort to vertical motion. We need to ask ourselves, how long does it take for an object launched with this specific vertical upward velocity to reach a displacement of delta y equals 30 meters? To calculate this, we can use the kinematic formula, which is the vertical displacement delta y equals Viy, which is the vertical component of the initial velocity, multiplied by the time, plus 1 over 2 multiplied by g, which is the gravitational constant, then multiplied by delta t squared. Why do we use this formula? We are given that the delta y is 30 meters. We can easily solve for the vertical component of the initial velocity, Viy, and g is just a constant, which is 9.8 meters per square second. Then we can solve delta t by solving this quadratic equation. So now let's find that vertical component of the initial velocity, Viy. Remember, our initial velocity is 45 meters per second, pointed at 35 degrees from horizontal. If we imagine this as a right-angled triangle, Vix is the side adjacent to the 35 degrees angle. Viy is the side opposite to our 35 degrees angle. So using our trigonometric ratios, we get Viy equals Vi multiplied by sine theta, which equals 45 multiplied by sine 35 degrees. So if you punch that into your calculator, you'll find it's approximately 25.81 meters per second. Now let's plug all these values into our kinematic formula to solve for delta t. We have delta y is 13. It equals Viy is 25.81 multiplied by t, then plus 1 over 2, then multiplied by g, which is negative 9.8, then delta t squared. Now you have to be very careful with your signs here. Notice that we are using negative 9.8 for g because gravity is pulling the snowball downward. By doing this, we are inexplicitly defining the upward direction as positive. Since our initial vertical velocity and the 30-meter displacement are both upward from the launch point, they stay positive. But that gravitational acceleration has to be negative. Now if we move everything to one side and set it equal to 0, so we have 4.9 t squared minus 25.81 t plus 13 equals 0. To solve for delta t, we'll use the quadratic formula. So if we have a quadratic equation, ax squared plus bx plus c equals 0, the roots can be expressed as negative b plus minus the square root of b squared minus 4ac, then divided by 2a. So in our case, a is 4.9, b is negative 25.81, and c is 13. When we plug them in, it gives us two possible values for delta t. One is 0.56 seconds, and the other is 4.7 seconds. So delta t1 is 0.56 seconds, and delta t2 is 4.7 seconds. We know it's not going to land on the roof when it's still on the way up. So we are only interested in that second moment, which is at the time of 4.7 seconds, when the snowball is descending towards the roof. Now that we have the time, we can finally use our horizontal formula to find out just how far this snowball travels during that 4.7 seconds of flight. But before the calculation, we need our horizontal velocity, Vix. If we go back to that same right-angled triangle we used, Vix is the adjacent side to our 35 degrees angle. So using the cosine ratio, we can get Vix equals Vi multiplied by cosine theta, which equals 45 multiplied by cosine 35 degrees, which is about 36.86 meters per second. So let's put them all together into our formula. Delta x2 equals Vix multiplied by delta t2. We have our constant horizontal speed of 36.86 meters per second and multiply it by our time of 4.7 seconds. If you do the math, you get a horizontal displacement, or delta x, of approximately 173.2 meters. Looking back at our landing zone, delta x2 must be within the range of 150 meters to 185 meters. Because this 173.2 meters falls right in that range, we can conclude that yes, the snowball lands on the roof. Alright, so that's the answer. Now, before we finish, I want to point out that there's actually another way you could have tackled this. Instead of solving for the time it takes to reach a specific height, you could look at it from the perspective of horizontal distance or horizontal displacement. You could ask, where is the snowball vertically when it has traveled exactly 150 meters? In other words, you could calculate delta y at the moment delta x is 150 meters. If you find that the snowball is higher than 30 meters at that point, it means it's cleared from the front edge of the building too. Then you just need to check the height again at the far edge at delta x equals 185 meters. If the height is still above 30 meters, it means the snowball flies over, right? If it's below 30 meters, it means the snowball must have landed on the roof somewhere in between. It's a slightly different way of looking at the same geometry, and it's going to be a great practice to try solving it that way on your own just to see if you get the same result.